Welcome to this lecture on architecting the self-healing CI pipeline. The core idea in this deck is simple, but important. AI has accelerated how quickly teams can write and change code, while continuous integration and delivery systems have often remained the constraint. When code generation speeds up, build failures, test failures, infrastructure errors, and dependency issues arrive faster too. The goal of a self-healing pipeline is to move beyond passive alerts and manual triage, towards systems that can detect a failure, understand its likely cause, propose or apply a fix, and validate the result before the developer loses meaningful time. The first comparison sets up the bottleneck. AI-assisted engineering creates a volume paradox: more code, more commits, and more build events. The slide calls out a resolution generation gap in the tens of millions, showing that traditional manual diagnosis cannot scale linearly with AI-generated work. The second pressure is time. A single failing CI run can consume around 20 minutes of developer attention, even before the team knows whether the failure is caused by code, environment, tests, or infrastructure. The third pressure is financial. The slide estimates hundreds of thousands of dollars in annualized cost from blocked engineering work. These three forces explain why CI remediation is becoming an architecture problem, not just a developer productivity concern. The next slide reframes the evolution from reactive debugging to autonomous remediation. In Phase 1, teams rely on post-failure manual investigation. A developer reads logs, searches build output, reruns jobs, asks teammates, and eventually patches the issue. Phase 2 is predictive transition. Telemetry and pattern recognition start identifying failures before the developer fully investigates them. Phase 3 is self-healing. At that point, AI does more than summarize the failure. It analyzes root cause, generates a validated fix, and automatically applies the correction when policy allows. The key distinction is that the system does not merely describe the problem, it closes the loop. Now we deconstruct the anatomy of a self-healing pipeline. The deck presents 4 core stages. First is detect and filter. The system extracts relevant error signals from thousands of lines of noisy infrastructure, compiler, and test logs. Second is root cause analysis. The pipeline synthesizes the error with repository context, historical failures, dependency state, and environment metadata. Third is solution generation. A retrieval-augmented or code-aware model generates a targeted correction, a dependency change, test adjustment, configuration update, or code patch. Fourth is execution and validation. The fix is applied in the live branch or a controlled pull request, then retested before it is considered successful. This is the universal baseline framework underneath both products in the deck. The comparison then introduces 2 paradigms for automated resolution. LogSage is presented as an enterprise framework, proprietary, staged, and designed for controlled deployment in internal environments. It emphasizes validated, auto-fix workflows for large industrial systems where compliance, data boundaries, and private knowledge bases matter. GitHub is presented as a cloud-native SaaS option, easier to plug in, integrated with public GitHub-style workflows, and oriented around zero-touch automation. The distinction is not just product branding. It is a strategic choice between deep internal control and broad, fast accessibility. The diagnostic engines diverge in how they understand failures. LogSage uses a multi-route retrieval approach. It pulls from active documentation, historical fixes, quality assurance plans, and failure corpora, then routes the diagnosis through a root cause synthesis layer. This is optimized for environments where previous incidents and internal documentation are valuable assets. GitHub, by contrast, behaves more like a contextual codebase engine. It ingests the failure log, cross-references the relevant repository, and builds a graph of relationships around files, tests, build scripts, packages, and recent changes. LogSage begins with curated institutional memory. GitHub begins with live codebase context. LogSage's token preprocessing pipeline explains why filtering matters so much. Raw CI logs are rarely model-ready. They contain repeated lines, irrelevant warnings, timestamps, stack noise, dependency chatter, and environment output. The slide shows a funnel that starts with filtering, moves through expansion, then finishes with primitive extraction. The stated constraint is a maximum of roughly 22,000 tokens. The impact is substantial. The deck claims token consumption can be reduced by more than 85% compared with sending the full log to a baseline language model. This is a critical pattern for production AI systems. Before asking a model to reason, first shape the input so the model receives the highest signal evidence. Execution is where the philosophical split becomes practical. LogSage keeps a human in the loop. The system invokes specialized internal automation tools, presents an interactive tool card to the developer, and requires explicit confirmation to execute the fix and re-trigger the pipeline. That design is appropriate when the cost of a wrong change is high, or when governance requires traceability. GitHub sits further toward full autonomy. It supports configurable automation levels, can operate in suggestion mode, and can also act directly. For eligible failure types, it automatically commits working code to pull requests. The real design question is not whether autonomy is good or bad, it is which failure classes deserve autonomy and which require review. GitHub's infinite validation loop is the mechanism that makes stronger autonomy possible. The loop begins by generating a proposed correction from the log and repository context. Then it validates the candidate against the user's specific CI environment before making a commit. Finally, once the fix passes, it applies the validated working code to the pull request. That loop matters because generated fixes are only useful when they survive the same environment that caught the failure in the first place. In other words, the validation environment becomes the judge, not the model. This is a strong principle for AI engineering workflows. Let the model propose, but let the system of record verify. Deployment environment is another major trade-off. LogSage is designed to be infrastructure agnostic but validated heavily inside closed, proprietary systems. The slide shows a bridge between hyperscale infrastructure, the LogSage core, internal enterprise toolkits, and documentation repositories. That gives it power in complex private environments but also raises the cost of setup. GitHub uses a plug-and-play architecture with a quick installation path through a GitHub app and native support across the public ecosystem. The slide highlights integrations such as GitHub Actions, GitLab CI, Circle CI, and BuildKite. So the question becomes, do you need deep integration into a private enterprise platform, or fast coverage across common CI providers? The operational impact slide gives the argument numbers. For LogSage, the deck claims over 1 million CI pipeline executions processed, more than 80% end-to-end precision maintained in industrial deployment, and support for tens of thousands of developers in a single enterprise system. These numbers position LogSage as the scale and precision option. For GitHub, the deck emphasizes reduction in manual CI debugging time, daily developer debugging overhead that can add up quickly, and zero-day detection for high-severity security vulnerabilities in generic tools. These metrics position GitHub as the speed and security option, especially where teams want immediate relief without a long internal implementation cycle. The economics slide translates remediation into return on investment. LogSage requires a proprietary industrial framework, custom engineering to build, deploy, and index internal knowledge bases, and optimization for hyperscale enterprise return. That means the upfront investment is higher, but the payoff can be significant where developer time is expensive and failure volume is massive. GitHub, on the other hand, has an accessible SaaS profile, public repository features, an unlimited public scanning model, trial-based autofix capability, and instant access without infrastructure management. The benchmark line suggests autonomous CI autofixing can save roughly $750,000 annually for a 20-developer team by recapturing lost debugging hours. Whether that exact number fits your team depends on build volume, engineer cost, and failure frequency, but the economic logic is clear. The definitive comparison matrix condenses the whole discussion. LogSage uses a multi-route retrieval augmented architecture. Jitar uses a codebase context engine. LogSage executes through interactive tool cards, while Jitar can issue direct pull request commits. LogSage's validation process depends on developer review. Jitar performs CI environment pretests. LogSage integrates through custom enterprise databases. Jitar integrates through GitHub, GitLab, and CI platforms. Access also differs. LogSage is an internal framework, while Jitar is SaaS with a free tier. This is a useful selection matrix because it avoids treating self-healing CI as one category. Different organizations will choose different points on the control versus autonomy spectrum. The broader autofix landscape places both products on a map. One axis is diagnostic depth, moving from simple diagnostic-only tools to full execution. The other axis is ecosystem openness, moving from closed ecosystems to platform-agnostic coverage. Jenkins plugins and GitLab Duo sit closer to diagnostic or ecosystem-specific positions. GitHub Copilot Autofix is powerful but is strongly tied to the GitHub environment. LogSage sits high on diagnostic strength with enterprise constraints. Jitar sits near high flexibility, high setup time savings, and stronger platform automation. This slide is useful because it reminds us that the best tool is not always the most autonomous one. It is the one whose operating model matches the team's governance, repositories, and CI topology. The final slide names the new baseline for software delivery. The paradigm shift is that AI in CI/CD has moved beyond diagnostics. The new baseline expectation is automated, executable remediation. The choice is between control and accessibility, LogSage for hyperscale, bespoke infrastructure control, Jitar for immediate, cloud-native auto-touch or zero-touch resolution. The future state is a self-healing autonomous CI/CD pipeline where failures trigger root cause analysis, generate fixes, validate them, and recover forward. For engineering leaders, the takeaway is to start classifying failure types today. Some failures should remain human-reviewed. Some can be safely suggested. Others can be fully automated. That classification is the foundation of a practical self-healing pipeline. To close, remember the central architecture lesson. Self-healing CI is not a single model call. It is a pipeline: signal extraction, context retrieval, cause analysis, patch generation, validation, policy control, and measured feedback. The slides compare LogSage and Jitar because they embody two credible paths. One path optimizes enterprise control and institutional knowledge. The other optimizes cloud-native access and autonomous pull request repair. The winning implementation will combine the right level of autonomy with rigorous validation, because in CI/CD, trust is earned by passing the pipeline.